officially welcome everybody. So not happy garbage day, happy Thursday. Let's see, you should have, your next formative assessment is available. I fixed it so it has a due date as opposed to an end date or whatever. I had clicked the wrong button before. And then we have one more week of classes until it's presentation season. So those of you who are going first, group one, you know who you are, right? You're getting it over with. That's your task, and setting a good example for your peers. So let me know as things progress if you need to chat about any strategies or if you run into convergence problems, that kind of thing. Any questions about that right now while we're on the topic? Nope. Taylor, I read an article over email this morning that I thought might be your lab. It was about like sleeping in babies.
Yeah, I think so.
Yeah, I was like, hey, I know that project. I'm going to hear all about it in a couple of weeks. It's very cool. Let's see, in the psych department, when I did this class 2 years ago, there was a student from the Growing Words Project from psychology, and my son had just finished participating in that, so I think I helped analyze his own data. So, small world. Anywho, we have lecture 5 to talk about and example 5B to start. How's that sound? And our roll call, we got one roomer today. We got 6 Zoomers. We'll see if anyone else joins us, but that's all right. I'm going to start on slide 8, if that's all right, because we're changing gears a bit. So this is slide 8 of lecture 5. So conceptually, this is a conceptual diagram, not a path diagram. This is the type of model that we've been looking at in example 5A, where there's no random change, so it's just within-person fluctuation over time. And we looked at how this would play out in a mediation framework. If all 3 variables are measured repeatedly, then you can have mediation at level 2 among the intercepts, and you can have mediation at level 1 among the E residuals. We are heading into the next section then is time-varying predictors that need multivariate models because they change randomly over time. So we've talked about this a little bit, but the key idea here is that if there's individual differences in change over time, at minimum, that's one more source of what we're calling between in terms of differences. And so that's one more variable that would have to be represented for each outcome for which there is random change. So there's no more just between versus within. It's between what? Between intercept, between change, between linear change, between quadratic change, between piecewise change, like whatever kind you have. So when that happens, it is no longer sufficient to think about between-person differences as mean differences, because if people change differently, they rearrange themselves. So you'd end up with a functionally different variable if you measured at one occasion, for instance, versus another. So intercept is no longer just the mean over time. It has to be conditional on wherever you've set time 0. So that brings us to the big circles here. So this is essentially example 5B. This is the core idea of it. We have 2 different kinds of between variation, and that means in terms of mediation and other stuff, there's more options, right? Because we could have intercept to intercept to intercept. I could have change to change to change. I could have intercept to change to whatever. I could have change to whatever, like all the permutations at level 2, when there are 6 circles that you could go between, essentially, if you had 3 variables that change systematically and randomly over time. So we looked at pictures before, types of relationships that we're going to examine between person and within person. Within person is illustrated by this kind of picture, where after you detrend for what is happening in terms of change over time, the question would be, do 2 outcomes have residuals that correlate over time? So if I'm above my line on one variable at a particular occasion, am I above my line on a different variable at the same occasion? Like the phrase that I've heard for this is travel together. And this can happen concurrently, or it could have a lagged effect. Like if I'm higher this time on one variable, then that shows up next time on the other one. That's a very common type of hypothesis that people have. So I think we talked about these, the idea of fixed change. You can compare which outcome changes more, but we're focusing more on the individual differences. So do people who start out higher in this variable start out higher on that one? Do people who change more on one variable change more on the other? That's the kind of questions we can answer. Did that in the context of repeated measures, and we talked about this a little bit too. So whenever you have random change in a time-varying predictor, if you just do some kind of person mean centering for it, it's not going to be sufficient. Because what you really have are 3 different sources of variability, 2 of which are between and 1 is within. But if you put a box around it, so this is meant to convey like what the contents would be of a person mean variable, It will be the intercept variance as intended, but it's also going to be a little bit of the within-person residual, because that's the part that would be there on an expected basis just from sampling fluctuation. This is the piece that gets removed when you treat it as an outcome, because the true amount of differences is corrected for the expected amount from the within-person variability divided by level 1n. So that's like this little piece right here. So when you put a box around it, this is still here. When you make it latent, you're isolating it just to this one. So that's one issue. The other one is that where would the change go if you haven't parsed it apart? Well, it's still in the level 1 variable. So then what I'm thinking of as within-person deviations is most of that, but then it's also whatever extent of between-person differences. So it's not really just straight within. Okay, does that idea make sense? Okay, because that's a key thing here. So this idea that you have this level 2 part that's still buried inside the level 1 variable is another kind of smushing problem. I call it time smushing, as opposed to intercept smushing, which is what we've been talking about up to this point. So I did a simulation to illustrate this, and this is from chapter 9. I also have a paper under review that takes this and expands it into further context. But the key idea here is, what if we start with person mean centering, and in a univariate model for a time-varying predictor? That's the model we're going to fit as an analysis model. But what generated the data was a multivariate model in which there were correlations among the intercepts, correlations among the change factors, and correlations among the residuals. So then the question is, how do those things interfere with recovery if you fit a model in which between-person change is not a separate thing? So the first plot here is showing what happens to the change in the random intercept variance after adding level 1 and level 2 effects. So if I add person mean centered level 1 predictor, I add in the person mean at level 2. And on the x-axis here is what happened in the population model. So what was the truth? What was the actual intercept correlation varying from -4, -2, 0, positive 0.2, positive 0.4. And then the different lines are what the population model had for the within-person residual correlation. So what happens then is that if they match, it's fine. If they match in sign. Like if everything is 0, right here, all is good. But otherwise, to the extent that they don't match, you end up with a different result. So even though the change in the random intercept variance should have had just an effect of the level 2 person mean causing it, you get more variance reduced when the within-person relationship is heading in the same direction. That shouldn't happen. So it's evidence that what we're calling like between person has a little bit of within in it because of that box not having a clear all the way partitioned between person intercept out of it. So that's one thing. If we look at like the triangle, for instance, a residual of correlation of positive 0.2, that then explains somehow more of the random intercept variance than if the residual correlation was a negative 0.2. That shouldn't happen. Down here, we see the same sort of story. So in this case, we are looking at the change in the random slope variance for the outcome after adding a level 1 effect. Shouldn't change, but it does. And it's the same idea. If the slope correlation, the true one here, ranges from negative to positive, the conditions in which the residual correlation is in the same direction result in explaining slope variance. The conditions in which the residual correlation is in the opposite direction actually make the slope variance go up. So it's evidence of a smushed effect here, because what happens at level 1 should not predict change at level 2 in the outcome, and it is. So, conclusion, don't do it this way. So in your project plans, I think I wrote this to pretty much every single person who has time-varying predictors. If you have random change in your time-varying predictor, you cannot use person mean centering. It does not fully partition out all the between sources from all the within sources. We need a multivariate model to do that. The only question then is, how do we set it up, and what does it mean? One more rumor, hello. All right, how are we doing so far? I'm back on the caffeine today, because it's that kind of day. I know this is sort of a complex topic. And if it's not clear from what I'm saying here, I would recommend either reading chapter 9 or reading the paper that's on your reading list that's under review right now. The papers are all in Icon, by the way, under readings. You don't have to track them down individually. Okay, no questions? So this is the idea. Time-varying predictors that change over time need to be predicted as outcomes, even if you're thinking of them as predictors. That's my main point. Now, what I want to switch gears to is, what do people do, and do they obey that principle when they do it? Spoiler alert, they don't. So this is slide 16. What not to do with longitudinal data? Wide data SEM version. So misspecified path models for longitudinal data are still the most common alternative that I've seen in practice. And these sorts of models are often designed to examine what are known as autoregressive effects. So that's like one variable predicting itself over time. Cross-lagged effects, which is like my x at time 1 predicting my y at time 2, my y at time 1 predicting my x at time 2. And when I use that term, I always make this gesture, like, because that's what the path model looks like, is you have these crossed effects that form these x's. And we would have multiple occasions, hopefully more than 2, but I've seen this done with 2 as well. So I wanted to show you some common examples as what to watch out for and what we can do instead. So the problem in each of these cases is the lack of differentiation of between-person variance and change over time, as well as with between-person variance and intercepts in some cases, and then what do the level 1 paths actually mean? We'd like to think of them as within-person effects, but if all the between-person stuff hasn't been detrended out of it, then they're not just going to be within-person, they're going to be partly between to some degree. And what is especially troubling about this, in the SEM literature, if you're in wide data SEM, that means you're pretending that your outcomes are balanced in terms of the timing of them. So let's say that you have balanced time, a few of you do. You can fit a model that is completely smushed and makes no sense and have it fit well. Like, having good fit does not mean that you've avoided smushing or misspecification. It doesn't. There's one of the other papers on your reading list, Hoffman and Hall, someone from Florida that I collaborated with for school psychology. I simulated data in which it was a multivariate model, like the time that we just talked about, correlated intercepts, correlated slopes, correlated residuals, and fit some of the more popular longitudinal path model-y things. And I was able to get good fit, even though it was completely the wrong model and the estimates were completely wrong. Because parameters can be compensatory for each other. And especially when you have multiple variables in a problem, they can prop things up in a way that is unexpected, but effective. So that's the tricky part, is that fit doesn't tell you necessarily that you've gone awry. So here's what not to do. Let's pick on the R. Levon manual first. It's still up. I just stole this picture. I've been doing this for years. So this is an example of how to fit a model with time-varying predictors in Levon. So I've got these variables here that are my outcome. They're called T, apparently. And I've got an intercept factor and a slope factor predicting them. It looks like I've got a box x1 and a box x2 that are predicting the intercept and slope factors. So that would make it a level 2 time invariant set of predictors here. And then C1, C2, C3, and C4 would be whatever C is measured at each occasion. And we have direct effects going there. So what do we think about this? Is this the within effect, the between effect, change effect? Yes, it is. Yep. Nope. So T is okay, right? T has the variances that are not shown in the diagram, but the variances of each of these observed outcomes would be the level 1 residual variances in your R matrix. Level 2 intercept and change variances in G would be here. But we don't have a parallel process happening for C. So these paths, even if they're not constrained to be equal over time, are smushed. Not to just pick on Levon, here's the M+ manual. Yeah, go ahead.
So, is it kind of like you need another matrix, like to separate it out then? Like if we're talking about T in the R matrix and then S in the G, like, are we essentially adding some sort of other matrix to try to partition it?
We are adding them to the matrices we already have. So in this picture, these variables would not be in the likelihood unless you brought them in. They would be treated as observed predictors, so the model wouldn't try to figure out their means, variances, or covariances, and that means you couldn't have missing data. If you brought them into the likelihood, then their means, variances, and covariances are model parameters. So to do this properly, if C shows random change over time, it gets its own I factor, it gets its own S factor, and they would live in the same G matrix as the ones for the outcome variable. Likewise, once it is predicted by intercepts and slopes, the leftover variances for each of these observed outcomes would go into the level 1 R matrix. So it just grows, to answer your question. It's not a separate one, it just expands. Okay. Other questions? So what I was going to say is I'm not just going to pick on Levon, I'm going to pick on N+. This one, still current, is a little different. It shows explicitly in the picture, different letters, but it's the same setup. I've got an I and an S predicting some outcome, now it's a Y. I've got an X1 and an X2 as time invariant predictors, it looks like, because they're predicting the I and the S. And I've got A measured repeatedly over time. Now, the fact that we have covariances among them, I think is meant to indicate that these are part of the likelihood. Because if you try to estimate covariances among predictors, that automatically brings them into the likelihood as outcomes. If they were to be correlated with the I and the S factors, then these paths right here would be within. But because they're not, these paths are still smushed. So we don't know what this means, in short. It could mean a bunch of different things. So what should we do? Well, this is the first idea. If we bring, now we have a different letter, sticking with Y, but now we're at Z. Still, and this was like some other letter, so I wrote over it with I and S, because, I don't do Greek if I don't have to. Now the Z's are correlated with the intercept and change factors. So that means that these paths labeled gamma are going to be the within effect. Okay, it's unsmushed. I can live with that. But what's not here? If I want a within person effect, I probably want something to go with it, maybe. What might go with it? Between. How's that getting in my picture? Can you guess how I might respecify the model to get it into my picture? It turns out that it's sort of buried in here through the correlation. Like you can rearrange it algebraically to get it back out, but no one wants to do algebra if they don't have to. Can you anticipate from this picture what the right answer would be? Any guesses?
Does it have to do with changing the coding?
Changing the model. Taylor, you're going to say?
I guess I was thinking maybe lines from the Z's to the, slope and intercepts, or maybe the other way around, but something like that.
Something like that, yes. If you can put lines from the Z's to these, but in general, you don't want a level 1 thing predicting a level 2 thing. You want, what would happen is that it would be the level 2 part of Z that predicts the level 2 part of Y. So the solution is to separate that out, to make the level 2 part of Z a thing that can then have its own relationships in the model. In other words, give it its own circle. So that's where we're going. Here's what may not work. Well, why can't we just stick in person mean Z as a box? Turns out if you do that, M+ gets very mad at you. And other software just flat out won't run. So that kind of model would look like this, where I might have, say, person mean centered time varying predictors down here because I don't want to do any smushing. I might put in the person mean, and if I fit this kind of model, it says the sample covariance matrix of the independent variables, meaning predictors, is singular. Model estimation terminated normally, but the chi-square is negative. Doesn't sound very normal to me. The log likelihood values may not be reliable. Cool. The problem is that this is redundant, essentially. Ipsitive is the term for it. So this is not the right answer. The right answer would be essentially all the way back, this idea. We take whatever we're going to call the time varying predictor and we predict it too. All right. So when would you want to do this? In addition to just not getting the wrong answers, there are particular types of research questions this would lend themselves to most nicely. So one, to fully disaggregate between person and within person sources of variance and their corresponding relations across variables. So you have to have variance of each kind before it can predict other stuff or be predicted. So it's useful as an outset to make sure that you understand what kinds of between-person variance you have in each variable in your model, regardless of whether you're thinking of it as a predictor or an outcome. Because then that logically dictates what it can possibly do in your model. Like if you're thinking of individual differences in change over time in X is going to predict some outcome, and it turns out you don't have individual differences in change in X, you're not going to predict some outcome. So logical prerequisites, what kind of variance do I have, and then what can it do? So you can prevent both kinds of smushing this way, intercept smushing and time slope smushing. That may happen if you're using observed variables instead. You might also want to do this if you intended to fit a curve of factors model. So that's the one where you have indicators of a factor, and the factor is measured at each occasion. And you have to have at least some level of invariance to hold that together, to say it's the same factor over time in order to measure change. If that falls apart, this sets up the idea of an alternative that we can examine change in each of our indicators and then see how related the indices of change are. Another one would be to examine autoregressive and cross-lagged effects. So this is that idea. And then longitudinal mediation would be a third use case in which you might want to do this. So we'll talk about a few examples of each. All right, so first things first, a recipe or a flowchart for you. First things first, we want to ensure that we understand univariate change for each variable measured repeatedly separately. We don't want other variables getting in the way and propping stuff up. So regardless of whether you're thinking of a variable that's measured repeatedly as a predictor or an outcome, you want to fit in some kind of unconditional model for change. The only catch is that how we do this depends on which type of model you're fitting. So I tried to break this down in more detail this time. Hopefully this will be useful to you as you're working on your data. So step one, estimate saturated means. Remember that? What am I saying, like concretely? How would I get a saturated means model? What's the idea of saturated means? How are you thinking of time in that kind of model?
It has its own variables on place in the model, so I don't think we did piecewise slopes. We had to plug the time back in. Is that?
We tried to saturate the model to get to test its fit. But yes, we're trying to get back to the answer key. There's your tip. Answer key model. Remember that phrase? Yeah, that's what we want. We want the answer key for what the fixed effects of time are supposed to be doing. If you have balanced data, then you would add occasion as a categorical predictor. So if you're in MLM, meaning you're using like Stata mixed or Elmer in R, then it would be I dot in Stata mixed. It would be using it as a factor variable most easily in Elmer. And if you have unbalanced time, you might need to round time into convenient intervals to be able to do this, but you wouldn't use those intervals or the fit of that model as a point of comparison. This is just for descriptive purposes only. So that was what we did last semester. If you're doing MSIM, you have to do this on a more manual level. There is no such thing in M+ as a factor variable. You have to make all the contrast yourself. So you would have to create basically a binary contrast for each occasion, estimate their slopes, and then you can put a saturated means model back together out of that. It's a little bit annoying. Less annoying, but also sort of weird to think about in SEM, is to just estimate the intercept or mean for each variable. So that was the part that we get shut off in SEM when we add change factors. Just estimate it. And there are certain kinds of path models where this is what happens. They just estimate the intercept, and then it's like, okay, here, what's the mean at this occasion? What's the mean at that occasion? And it's a mean per separate box. So this would hopefully guide you then in conjunction with whatever the study is about as to what kind of model of change that you would have. So let's see. Emily, I'm going to call on you, okay?
All right.
Okay, in your study, you have pre and post COVID, right?
Yep.
Yep, so what kind of model are you going to fit for that?
Piecewise.
Bingo. COVID is a big natural event that gets in the way. One might quibble about when COVID happened in terms of how long it lasted and when it ended, since, you know, people still get COVID. But there's a clear event that would, like, what was changed like before, what was changed like after. Let's see, Ryan, you showed me a picture yesterday. I'm calling you too.
Yes.
Yes. So what outcome is changing over time in the picture you showed me?
That's the traffic volume for like a certain road, from like, during 24 hours during a day.
Okay, so once an hour, we have a measure of how busy the traffic is on a certain road. What kind of
Yeah.
what kind of shape did it have?
It has like a curvature, it's like a bell shape. If I move like, 0 to 4 a.m. to the end, like I start from like 5 a.m. in the morning and recorded until, like 4 a.m. in the morning, then it's like a bell curve.
Yeah, so traffic starts picking up around 5 a.m. It gets steadier and steadier throughout the day and eventually starts tapering back down, and then eventually people go home. So in that case, I don't think piecewise would be as useful as something like quadratic because it's sort of a smooth function. There's nothing magical that happens in the middle. So like both of you have, I think, probably similar looking profiles potentially, but I think in Emily's data, it would make more sense to have a piecewise model because there is this demarcation that happened from COVID, whereas there's no clear demarcation that happens in like the day. So it's not just what the change pattern looks like on average, but also kind of conceptually like what is causing change and what would be a reasonable way to think about representing that as a theoretical process, not just an observed pattern. So a little bit of art, a little bit of science. But this is how you would do that in the 3 different ways of thinking about it. And by the way, even if you're eventually going to end up using SEM or MSEM, you can do these initial steps using R or Stata. It's fine. Don't make it harder than it needs to be. Next step, what kind of variance pattern do you have? So univariately for each variable still, if possible, some kind of unstructured matrix. So we want to know what the answer key is with respect to what the random slopes for change over time are going to be doing. And this one you may not be able to do. So this is only for balanced data or rounding it into balanced data, and only for studies that have relatively few occasions. Otherwise, it will be too big of a matrix to estimate everything at once, especially if you don't have large sample sizes. So if we're in MLM, this is super easy. Unstructured R matrix directly in mixed. In R, you would need to switch to the package NLME, and they have a function GLS within that. That's the only way that I have found that you can estimate models without random effects, because this would be an R-only model at that case. In MSIM, I don't know how to do this. If it's possible, you would have to go through a significant amount of trickery and hacking to do it. So don't do it. SEM, it's done for you. That's the H1 model. If you ask for SAMP stat, it will print the variances and covariances for you. And they are what is estimated using maximum likelihood, not the observed data. So it is exactly what you want. So I would do it that way. And requiring balance time as an aside, because we're assuming that every spot in the matrix is separate. We don't have individually varying occasions in that case. If you do not have balance time or it's too far unbalanced, you can skip this step. You'll just have to live with the fact that there's no answer key to come back to. And that's why in most MSEMs, they don't even show any kind of fit statistics other than just the log likelihood in AIC and BAC, because they don't assume there's an answer key, assuming it's unbalanced. Okay. Once you have whatever fixed and random time slopes are needed, so based on these patterns, based on what happens when you compare models, keep in mind that you can use likelihood ratio tests to judge the significance of random things. You cannot use it in REML to judge the significance of fixed effects. So do not compare models that differ in fixed effects in REML. So then you can consider what your R matrix needs to look like. Do you need heterogeneous level 1 residual variances by occasion or not? If you're using MLM or MSEM, the default is that they're all the same. If you're using SEM, the default is that they're all different. So they're starting from different reference points. So in MLM, you don't have as many choices. All of the software that I know of is either all different or all the same. There's no in-between option. In MSEM, same answer. I don't know how to do this because there really is no R matrix to speak of, no way of specifying it directly. In SEM, though, you can do this. And so you have what are known as modification indices. I call them cheat codes because it's like if you have a magazine that tells you where all the points are hidden in like a video game or something, you don't have to go and find it out. It's cheat code. It will tell you, hey, you know, if you free this residual variance, it'll improve your model by that much. And then you can customize it. So maybe the last one needs to be free and the others can be the same, or the first one and the last one. Like however, whatever pattern it ends up needing, it can tell you what's needed and help you figure out what to do. And then finally, level 1 residual relations. So for those of you who are doing like daily diary kinds of studies where it's like a lot of repeated measures, you may not have random change, but I'm guessing you're going to have some kind of residual relationship because occasions that are closer together are going to be more related just because they're closer together. So something like an AR1 structure, a LAG1 Toeplitz model where you just have adjacent occasions being related. In MLM, you can add this as an R matrix pattern. So this would need to be using either NLME or GLS because Elmer does not have this. It does not allow, this doesn't have the infrastructure for correlated residuals. In MSEM, the only way that I know how to do it is to make slopes, not covariances, meaning one variable predicts another, not just that their residuals are correlated. And that causes differences in interpretation. And in SEM, you can do this directly with residual covariances just by adding width. So I have many examples of that if anyone needs to see those. And we can also do slopes if you want to with something called structured residuals, which we have not talked about yet, but just putting a flag in that for right here. Okay, so questions or comments on this part? This should be mostly review, but just adding in how do I do it this way? Because it's tricky to figure out sometimes. Questions? No? Zoomers? Any that you want to hear again?
Sorry, I actually have a question.
Please.
I sometimes wondering how, when you just look at the data, how you know like there is an interaction or not, like, or you're just based on like empirical, like you think this makes sense that they have interaction.
You mean a fixed effect interaction?
Yes.
One way that could show up is heterogeneity of residuals. So if you were to output level 1 residuals or predict level 2 U's as the predicted random effects, if they don't have constant variance across a predictor, like if it looks like a bow tie, essentially, like it spreads out as you go out, that's usually a dead giveaway that you're missing an interaction. But to be able to ascertain that from a picture is very challenging. I think that you're better off just trying to think about which interactions would be logical or expected given your content, and then looking for them in the data. That's a more atheoretical approach, but it's also one that I think is going to be easier to work through reliably than looking at pictures. A long time ago, when I did an advanced version of a longitudinal class, it looked very little like this one, though. It's very long ago. One of my assignments was I made data with assumptions that were broken, and I made plots, and they had to figure out how the assumptions were broken from the pictures. That was a homework I made. Do you know how wrong the model had to be for it to show up in a picture that everyone could see? Like, it had to be the wrongest, dumbest thing ever. And that exercise taught me, like, no, like staring at residual pictures, like the ones you see in textbooks, no, they are never that clear cut in life. And it's also like, we're scientists, we're not going to do a Rorschach test. Like, oh, it looks like maybe it might be. No, no. So I'm not sure if that's a good answer, but I don't know of a way without looking for them to ascertain that.
That's good.
Okay.
Thank you.
No problem. Other thoughts or questions? Okay, so once you understand what is happening with each variable in your problem, whether it needs intercept differences, change differences, or both, what kind of change differences there are, because you might have more than one kind of change factor, like a before factor and an after factor, or a linear factor and a quadratic factor, then you can work on putting them all together into the same problem in a way that addresses your research questions and allows you to examine whatever effects you're curious about. So this then is an example of what one option might be if you had a variable that had random change over time, so that's y in this one here, and another variable that didn't. So z doesn't have random change. You don't need to put it in. It does have a random intercept though. And so now I have a way to get the between effect in the model. Look, int to int. Yay! I know that this is the between effect because of this intermediate layer here. This is a hack. Yeah, I know that face. Just wait till you see the code. It's epic. So this is a specification that is known as structured residuals, is what it has been called. This is, I believe, the original source of it. And what we're going to do is the same trick that we did for the mood intercept that wouldn't give me an interaction the other day, 2 days ago. And I had to move the intercept to a new latent variable and like move its information over. That's what we're going to do. We're going to make a new latent variable that is going to contain the information from the level 1 residual of each of these boxes here. And so then that new latent variable is going to do the predicting. Because this latent variable only has within-person information in it, this can only be the within-person path, and this int-to-int path becomes the between-person effect. That is the purpose of this intermediate layer of what looks like what? It's just moving the information out of y into here so that this becomes within and this becomes between. If you skipped it, I think I took out that picture. If you don't have this, then it's all of y that's predicting z, and then that becomes within, but this one is contextual. And that's what we had in the previous example as well. So the reason to do this is so that you get between paths in your model and not contextual paths. I will show you an example of what this looks like. The good news is that the horrendous code that this used to take in the newest version of M+, they've made a workaround, so it's shorter and less painful. What if you have individual change in both variables? Then it would look something like this. So this is my picture. This is from somewhere. I don't remember where I stole it from, but I made it, as opposed to stealing someone else's. And this is x that is changing over time, has a time slope here, and then y is changing over time as well. And so now I have, these are directed paths from the intercept of x to the intercept and slope of y, from the change slope of x to the intercept and change slope of y. You can make these directed, you can make these covariances, it's up to you. And then I tried to do this, which reviewer 2 absolutely hated in one paper where I tried it, so I'm sticking to it. Rather than have each of the separate little like circles, I decided to make this like big circle rounded thing because all of their variances are constrained to be the same number. And then I wanted to have like these residuals are predicting the ones over here, but then they're all doing it with the same fixed effect that has no variance. That's the idea. So if you specify the relation from these residuals to these residuals, as opposed to from these boxes to these boxes, this is within and this is between. What if I had a third variable? Yeah, Hillary, calling on you now. How many time varying predictors are you going to try to put in your model? Like 6?
5 or 6.
5 or 6. Okay, so you're going to need a bigger slide.
Yeah. I'm gonna have to like break my model up into like multiple slides in my
Yep.
presentation.
Yes, you are. But it would be the same thing. So you can hope that some of them don't have individual change, because then that reduces the number of circles. But this is what would be needed. At a minimum, I would expect that data that involve people are going to have random intercept differences. If you're studying weather or rats or something else, maybe not. But I'm most familiar with people. So multivariate chains, use case 1. We do something like this. All right, yeah, more caveats. Things I've already said, but I'll say it again. If you don't have random change, you could use person mean centering instead. However, the level 2 effects that you get are going to be downwardly biased relative to what they would be when you do it with an intercept factor instead. And that's because of the incomplete partitioning of what the person mean has a little bit of level 1 in it. So it drags it the wrong way. I would say that at level 2, in these kinds of models, relationships can be covariances or they can be fixed slopes, meaning pathways that are directed, but that anything that predicts a variable's change should predict its intercept too. So if we think of this in terms of a linear models context, if I'm predicting change over time, how do I do that? If I want to say the intervention group grows more than the control group, what would that look like as a term? What kind of fixed effect would answer that question? Does one group change more than another? An interaction between what and what? Louder.
No, I'm thinking.
No, you're thinking. No, use it. It is an interaction. One of them's group. Time by a group. Ding, ding, ding. Yes, it is. So if I have time by a group, that's a two-way interaction, right? That means I need a main effective group and I need a main effective time. The main effective group would be the group difference at time 0. The main effective time would give me the slope for the 0 group, whatever they are. Okay, so it all works together. Now, if I keep those ideas onto these kinds of pictures, if I have a main effect of this intercept would be the intercept-to-intercept path. If I wanted to say if people who start out higher in X change more in Y, that would be intercept-to-change slope path. But that would be a cross-level interaction in a linear models context. So we would not want to have intercept to slope without intercept to intercept as the main effect. So there's logically different possibilities here. The intercept path would be analogous to a main effect of a level 2 predictor because it predicts the intercept, this gesture. The intercept predicting change over time in another variable would be analogous to a cross-level interaction, like group by time or level 2 intercept by time in this case. Then we can also have the change factors do stuff. So if I predict the y-intercept with the x change factor, that is analogous to a main effect of change in x. And if I have change to change, that is analogous to a cross-level interaction. So you can do whatever you want in terms of which way the arrows go or the covariances go, but just try to remember those principles because otherwise you can end up in a weird spot where you're essentially missing main effects but you have interaction terms. So would not recommend that. And then, of course, the big question, are these things between or contextual? It's going to get fun. That's my demonic smile. I didn't make this up though. If I made this up, this wouldn't be that way. Here's the answer as to when things are what. But it works in a very weird and unexpected way when you have these kinds of models with intercepts and slopes and residuals. That's the one thing I did not anticipate when I was first learning about this stuff, trying to figure it out. So here's some tips. If you're not sure if a given level 2 effect in your model is between or contextual, here are some ways we can figure this out. Start with the simplified version, in which each pile of variance for your outcome, which I'm calling y, is predicted by only one pile of variance for x at a time. So remove all the other slopes, just get one going. The goal of this would be to recover bivariate relationships between x and y without contamination of how the slopes would change after you add other predictors into the mix. Okay, so now we know what, like, it would just be, this is the straight between or the straight contextual. The concern is relevant whenever both variables have change slopes, or have slopes, that happen at both levels, level 1 and level 2. So for instance, if this is my model for x, and these are the variables that I would have as predictors, this is my model for y, and these are the variables I would have as predictors. If there is a within-person relationship that is directed in the level 1 model, then fixed slopes for at least some of what we're thinking of as between could actually be contextual. That's when we have to worry about this, is when we have a corresponding relationship at level 1 between two variables and at level 2. So how to check? Compare the level 2 slope results from two different models. Change the fixed slope between your two variables to be a covariance instead. That's how. Because the difference between and contextual, remember this is definitions? We'll go back to, this is January, I think, or maybe early February. A between effect does not control for what's happening at level 1. A contextual effect does. So if you change what's happening at level 1 and level 2 changes, it's got to be contextual. So between wouldn't care which of these you have. It should be about the same number, but within does. So I will show you that in example 5b as well. Okay, 29. Yeah. All right. How we doing? Questions? Sideways? Yeah. No questions? Anything you want to hear again?
I think it's always hard for me to know what I don't know until we do the examples.
Ding. Or you're trying to figure it out in practice, right? That's the trick. Is can you actually do this and make it work and know what you have back? So this is one use case, is just basically multivariate relationships. How do my intercept and change factors and residual factors all relate to each other and other stuff? That would be one. We talked about this, but just to remind you, curve of factors versus factor of curves. So lower order factors, creating a latent factor at each occasion. This is curve of factors. Higher order factors then are indicating change in that latent variable. This answers the question, do I have fixed and or random change over time in one variable? Like you're thinking of the latent variable as one thing, and that one thing is measured by 3 or more indicators. That assumes that each of the indicators would change the same way over time, like they all follow suit. This requires at least partial longitudinal invariance to make sure that the factor means the same thing over time. If that falls apart, then you could do something called a factor of curves. This is a multivariate model of change. So this goes by multivariate latent growth curve, this goes by parallel process model, and the factor of curves starts with that as its root. So it's the conceptual reverse. We start with change over time in each of our observed outcomes, or indicators as they would be called, and then we could potentially test higher order factors of change. So do the intercepts correlate in a way that is consistent with the idea of a single latent trait driving them? Do the change factors correlate in a way that is consistent with a single latent factor driving them? That's the idea of factor of curves. This is kind of a misnomer because it should be factors of curves, because you need an intercept one and a change one. but I didn't make the rules. That's just what they call it. So here's the pictures that go with that. This is curve of factors. This is factor of curves. So this whole upper part here isn't strictly necessary. You could just let all these intercept and slope factors covary and see what happens. Case 2, cross-lag relations. So all of the within-person relationships that we've seen are concurrent. It was like X today predicts Y today, or X this time predicts Y that time. Lagged within-person relationships can be examined, but in univariate MLM, it's a little bit problematic. One is that the first occasion gets dropped because you have to have complete rows. So if you're having the first occasion predict the second occasion predict the third occasion, there's nothing to predict the first. So that automatically gets dropped from your problem, whether you want it to be or not. The other is that you can only have it go one way. In univariate MLM, it's univariate. You're only predicting Y. So I can say, is there a lagged effect of X on Y? I can't then also say, is there a lagged effect of Y on X? So the wanting to do both at the same time is this idea of cross-lagged. That's where the term comes from. So to examine this, the model needs to somehow have access to all of the occasions at the same time. That's the tricky part. Although one can create lagged observed within-person variables, there's no comparable observed within-person variable on the Y side. So the cross-lagged interactions are easier to examine in Y data. That way you have all the occasions on the same row and you can do whatever you want among them. In MSEM and M+, the dynamic SEM, that's a new buzzword, that implies certain lagging features that allow these models to be estimated. It's the same issue of using centering to avoid smushed effects, even though it's not as obvious. And just having longitudinal paths is not enough. So, more on what not to do. Especially for cross-lagged kinds of questions. Does change in X predict change in Y? That's usually the way people talk about it. Misspecified path models are still very, very common. So here's some examples of common exemplars, but there's a whole lot more. So within the last 5 years or so, this world has exploded. Everyone and their dog has made up some new kind of model. And I would recommend these papers on your reading list to learn about those. Some of them are known as accumulating models instead, and those are really, really, really hard to interpret, and I don't like them. So I'm only showing you unaccumulating models because of that, but if you want to know more about that, please read these things. The problem in each of the pictures that I'm going to show is a lack of differentiation of their sources of variance, and thus what their slopes mean. So if the path model variables have not been detrended for person mean differences and for random change if it's there, all paths are going to be smushed to some degree, and this problem won't be reflected with bad fit. So this is a classic model. It is still really, really popular. It is either called the ARCL for autoregressive cross-lag, or it's called the CLPM for cross-lag panel model, or it's called the ARCLPM to put it all together. The key idea is this. At time 1, we have two variables that are related to each other. After that point, then we have last times X predicting next times Y, last times Y predicting next times X. We have last times Y predicting next times Y, last times X predicting next times X, and then we have covariances among the residuals at the same occasion for each of these other things. So this is the classic example. One of these articles on your reading list also, I think, does a really good job of explaining where the problems come in and also putting that into a contextual basis for childhood development. So the idea of this model is that we have controlled for previous occasions by putting them in as these fixed effects. So this is going to be what is change between time 1 and time 2 in X after controlling for time 1. That's the idea. However, by only allowing one path, usually constrained over time, it reflects smushed effects across all the sources of variance. So intercept, slopes, residuals. These AR paths do not adequately control for between-person differences. Now, you may not remember this because it was all the way in the fall, but I showed you in the The worst lecture, I think, it's my least favorite one to give ever, the ACS models, alternative covariance structure models, and the R and the G and stuff, that's one of my least favorite things to talk about. And you're like, yeah, same. But I don't know if you remember this. I gave you an example of an R-only model that was autoregressive, and I told you that I've never once seen it fit data. This is that. If we work through the logic of path models, the rules are, I can say that how y1, for instance, relates to y3 is I can say it's this path right here times that one. And if I want to know what the relationship is between y1 and y4, it's this one times this one times this one. Now, if I make all three of these the same number, like this is B2, the same label implies it's constrained to be the same number, then occasions 1 unit in time apart are correlated R. Occasions 2 units in time are correlated R times R. 3 units in time, R times R times R. Remember, squared, cubed, fourthed, fifth, that's this. So it doesn't fit data. Here's why you can think it looks like it fits data. Because in this picture, the relationship between, say, y1 and y3 isn't just these two. It's also this covariance times this path to get over there, and this covariance to go this way to go that way. So there's a whole bunch of stuff that's propping up the relationship between these variables that is the other variable over time, not just one by itself. So it can look like this fits, even though it really doesn't. Here is how to fix it to some extent. This is the random intercept version of this model. This is a picture that I made for another talk. Here are, I think, a list of choices. So this is the M+ website, has a whole page about this, of all the people who've published on this model. This is called the random intercept version because we have a random intercept for X, a random intercept for Y. By convention, they have a covariance usually, although this picture has a directed version because you're allowed to do that if you want. I have my observed occasions here for Y and X, but then I have the circles. So this is a structured residual version of the model where I move the level 1 residual variation out of each of these boxes and I put it in a new place. These new latent variables here are just taking this information and holding it for them, but it's only within person information if you do so. So then all of these cross-lag and autoregressive paths are within paths. The between paths are up here. So if I were to write this as a linear model type of equation, this is what it would look like. Notice that each of these observed variables would have an estimated intercept. Functionally speaking, that makes it saturated means random intercept with respect to what each variable is doing. So people who use this model say they've controlled for change, because each of these boxes has a separate intercept by which to allow the mean to change over time. Now, what do y'all think about that? If I let each variable have a different mean, have I controlled for change over time? Nope. What am I missing? Random slopes. Yeah, controlling for individual change. I've controlled for average change. So, can you guess what would be needed to do that? I think I see people typing. I'm going to wait patiently. More circles! Yay! Indeed, indeed. I have a picture, don't I? Yes, I do. More circles. Skipping a slide. Yeah. So this is the latent curve model with structured residuals. That name, that source. So we have, I don't know, I'm going to go with intercept and slope. alpha and beta, alpha and beta. Latent variable things in the middle here. So these are within, these are between, but now we have more circles. What if Z didn't have individual differences in change, but Y did? What do I do? Yeah, I just get rid of the slope for this one. So they don't have to match. But the key idea is that univariately, you would first determine what kind of between-person variance each variable that's repeatedly measured has, and then build your model with that structure in mind. They don't have to match. So I think that's the biggest issue that I see in practice. People fit this model and say, look, I controlled for between. No, you didn't. You controlled for between if there's no individual change, but not otherwise. Otherwise, do you know where it is? It's in here. So if you needed change circles and they're not in here, then these paths are not just straight within. There's some blend of the within path and the relationship between the change circles that are missing that should have been in there. That's what you get. How we doing? Getting there. There. That one. What did I say about that? Yeah. Same thing. What if you don't want to do this part? If you don't go to the trouble to put in these extra layer of latent variables, then these are still within, but these are contextual. So you don't have to do the structured residuals, and in fact, some types of models don't allow you to. In particular, let's do a crossover event with a generalized class. Okay. I'm going to call on, let's see, who am I going to pick on today? I'm going to pick on Erica. She's like, I knew it. What if X were binary? I don't have a residual variance circle in the first place. How am I going to do this? Not maximum likelihood, at least. In the weighted least squares world for M+, they've figured out a way to do this, but it sounds sort of sketch to me. But if you don't have, like this works for normal residuals only, where you would have a separately estimated residual variance. If you don't have that, then you can't do this trick. That's one example. If you wanted to throw some kind of other, if you wanted to make these paths random, M+ will throw up if you try to do that with structured residuals, I've found. But yeah, that's one thing that we haven't talked about at all up to this point. What if the extent to which last times X predicts next times Y within persons varies over people? Could we do that? Yeah. How? Say your previous answer again, Taylor. How are we going to do that?
More circles.
More circles! Yep. Because there'd be another layer of circles here that would be a variable that captures how related X and Y are within persons. That's another set of circles. In my example, I did not do that. Thought it was big enough, but you could. So lots of circles, lots of opportunity for circles. What if people vary in the extent to which last times X predicts next times X? Do you think some people are more consistent in their behaviors and responses than others? Possibly. That could be a random effect too. More circles! What if people differ in the amount of residual variance they have? That's a location scale model. More circles! Yeah. Lots of between stuff could be floating in here that could be separated and examined as well. All right. Did that one, did that one. Lagged effects. Oh God, I don't want to do that one yet. Okay. 139. No wonder I don't want to do that one yet. Question. Whenever it is convenient, can you please give me an example of what A and B might be? This is, I believe that this is going to be, A would be intercept and beta would be slope. This is from whatever system of notation they used in this paper. I usually write over these, but I didn't because I couldn't make them big enough, but that's what I think it would be. In reality, how would you know what these mean? Let's say you're staring at someone else's model because they know that you know how to do this stuff now and they come to help. They want your help. How do you know what these mean? If you're just looking at output or code. This is wide data SEM. How does time get into the picture? Time is stored as part of the variable name. How does it get in the picture?
You added like what time it is on whatever circle it is.
Yep, we constrain the loadings. So if I see a factor that has all the loadings fixed to 1, that's an intercept. Or theta in a Roche model. If I see a factor that has the loadings fixed to whatever occasion it is, that's a slope. And the pattern of the loadings tells me what kind of slope. Is it 0, 1, 2, 3, 4? That's linear. Is it 0, 1, 4, 9, 16? That's quadratic. Is it like -2, -1, 0, 0, 0, and then another one is 0, 0, 0, 0, 1, 2? It's piecewise. That's what yours will look like, Emily. Yeah. So I don't know what they mean without context, but the loadings are what tell you what they mean. And so you're forcing an interpretation when you set up loadings that way. All right, 141. Questions otherwise? No, we're overwhelmed, aren't we? Ding. Yeah, I'm clairvoyant. And I can read the room. This one and that one. But it's Thursday, which means we're done. So have good weekends. Let me know if you need anything, especially folks who are presenting soon. We got to get those things moving along. Yeah, that's it. Do your formative assessment, and I'll see you next week. Thanks for being here. Bye for now.